self-supervised or the unsupervised way of generating a graph. So this is, a different problem here that we're trying to solve, which means when we have self-supervised, okay, or unsupervised, it means that we don't have a target. So in self-supervised and unsupervised generative GNNs, we are solving a different problem because here we don't have no target corresponding, okay, ground truth graph, which means given, for example, given GS, generate GT. So we may not have GT here. So we don't have the correspondence here. We don't have that. So we need to learn how to generate in a fully self-supervised way, which means we only have the graph. This is similar to clustering, okay? So given the data itself, you want to kind of, use the data that you have to extract some meaning, to do some pattern identification, or here we want to do some generation, data generation or graph generation, okay? So this is very different from the early tasks that we have seen previously. So let's look at how we actually formalize this. So as I said previously, we learned that encoding graph structure, how to encode graph structure by generating node embedding. So we have seen this in graph classification. And this is based on the aggregation, the local aggregation, the computational graph that we have unfolded, the subtree computational graph, the transformation that we apply after the aggregation or before. So this was the first part that we learned about GCNs and different pooling and update rules and message propagation rules, etc. Okay. So now graph neural networks can also be used to capture feature information and also graph structure, okay? So what we can do, we can, for example, using graph encoders that we'll talk about in a bit, we can learn how to, map the graph to embeddings. And this is actually what we have done somehow. So we encoded the graph or embedded the graph. So this part has been, implemented or like explored previously, encoded or embedded, okay? A given graph G belonging to a set of graphs big G, okay? So now what we want to do, so this is, the encoding process. If we learn how to generate, how to define the opposite operation, which means now given, the graph embedding, we can use a decoder to transform the embeddings into graphs, okay? So, and this is what we will do. This is actually the generative power. So this is actually the generative power that we want to implement. So basically, given the embedding, so let's say given an embedding, sometimes they call it here Z, but if we call it HG, right, we can easily regenerate a graph G. So that's the idea here. And this is what we call decoding. So we decode the embedding into a full graph. All right. So this is what we want to do eventually. We want to generate new graphs from, like a certain compact representation. So this is one way of thinking or formalizing generative graph neural networks. So why generative graph neural networks are important? There are so many applications. So graph neural networks, they allow us, graph generation is a process that can allow us to understand how graphs form, how they expand, how they shrink, right? How nodes get removed, added, etc., right, in a dynamic way. We can also identify abnormal parts in the graph. So if you're working on network, cybersecurity networks, you can identify threats. You can identify, certain vulnerabilities in the network or even in the code if you're mapping the code onto a graph. So there are so many things, so many applications that you can do. Predicting new structures, if you're learning about, if you're, for example, using drug data, you can try to learn or predict a new structure of a drug that is able to treat a particular disease. And it's so difficult. You can spend, like months and years trying to do drug discovery, effective drug discovery. But using GNNs now, you can easily discover drugs, across a variety of applications. Well, of course, not always easy, but it takes less time, right? So now simulations of also, as I mentioned, novel graph structures, graph completion, which is basically trying to complete a graph where partially a partial part of the graph is available, which means partially here, it means, maybe nodes, a few nodes and edges are available. Okay, so I mean, there are so many things we can do. And one example here is to generate a new kind of molecule that cures a certain disease. So given a class of molecules like toxic and non-toxic, we want to, generate, we want new molecules that satisfy this class, for example, a particular class, okay? So we want to generate non-toxic molecules, for example. Now, the second thing is generate the dynamic evolution of brain connectivity graph. So see how the brain evolves over time to spot atypical alterations and that may be related or linked to neurological disorders such as schizophrenia or autism or dementia, right? So you can see here, it's so interesting to learn how to generate new graphs in general from a particular class, a particular category, etc. Okay. So now let's look at the basics for this self-supervised and unsupervised graph generation. All right, so first we start with the P data. P data is the data distributions, the graph distribution that we have. So here we can see we have molecular data, okay? So given P data, which is the data distribution, unfortunately, we can't actually measure it or define it in a very accurate way. So this is having access. We need to have access to every single instance of molecular data, for example, a brain graph, to cover the whole distribution, to all possibilities of the manifestations or the sampling of a brain graph. So we can't do that unless we have access to every single instance. And because we have limited data, we collect only a few samples, a few representations. This task is, hard to solve, okay? So actually, we don't know the distribution of the data, and it's a high-dimensional data. Remember, guys, like we have graphs or we have images. These are high-dimensional entities. So trying to kind of model that high-dimensional complex distribution is really not an easy task. And so basically here, P data is represented by the example, so in a reductionist way, by the example that we have. So the existing samples of graphs. So if we have these samples, the P data that we will just simply represent it by the distribution of the data that we have, which is the training data, okay? So here we can approximate it here by the training data. So this is the train data here, okay? So if you write here, so this is the train data, okay? So the training graphs. Now, the goal here, giving graphs sampled from P data of G. So G is like the graph that we want to sample. So we sample different graphs. And these are the sampled graphs from the distribution. So let's say, for example, this is the distribution of P data, okay? So this is the distribution. And what we want to do, okay, so I'm going to just copy paste it here. All right. So in this example, next, what we want to do is actually, we want to learn a good model, okay? So we want to learn a good model that represents the graph. And this means that if this model can recreate this data, can kind of, if this model is able to approximate this distribution, which means recreate similar graphs to this train set, right? So it means that these guys here that we created using the distribution of the learned distribution by our model, right, which is parameterized by theta, it means that we are able to approximate the data distribution that we have that looks like this. Okay, so let's say again, so basically it's actually very simple. Given the graph sampled from P data, we want to learn a model that represents these graphs. So we want to learn the distribution P model of G given theta, right? That approximates the training data that we have. And then after we learn this model, it's so easy. The second step is to basically identify how to sample from this model. So once we have the distribution, we want to generate new graphs. And to generate new graphs, we need to learn how to sample from this complex distribution. So P model here is the model parameterized, actually the model parameterized by theta that we use to approximate the distribution of the training data that we have. Okay, so that's, you know, a simple thing. So we want to create something. We want to generate a data that has a distribution. So maybe I can use a different color here. So let's use a different color, maybe green. Okay, so we want to generate a data here in the target domain by our model, and we hope that the distribution of this data will be close to the pink one. Okay, so if it is close, it means our model is quite good, and we are able to kind of, you know, to approximate very well the original data distribution, okay, that we have here. Now, one thing, how to sample, think about it. So you randomly draw, so you can draw from this distribution multiple values, and as you draw, this sampling process will allow you to create new sample new graphs. So basically what happened here is that we learned the distribution. We learned this distribution, the P model. We learned the P model G given theta, right? And then once we learn it, we can sample. And as we sample, we can create this set. Okay, so we can create all these graphs. We can generate all these graphs through the sampling. So sample or generate new graphs. So our goal is to basically, you know, learn this model that allows us to kind of match this original distribution. And once we do, we can use the distribution that we learned to sample and generate new samples. Okay, so I hope it's clear, guys. I know I've repeated it multiple times, but yeah, so that's the key idea. Now, let's detail this a little bit more further. So first, so as you guys can see here, we don't actually have a ground truth, which means each, you know, generated graph here doesn't have a ground truth to benchmark against here, right? So there is no matching, but our ground truth is actually, or not ground truth, because we don't have the ground truth. So our approximation is the P data that we have here. So the P data of G, and our goal is to match this, right? So this is what we want to match. And here it's like, you know, we want to be able to capture this distribution to the best of our capacity by optimizing the theta, the parameters of our model. And if we do that, we are able to generate new samples. And these new samples, how can we evaluate their goodness? It's a huge problem. So we're going to talk about evaluation later on. But the idea here is that you can think about, you know, the distance between these two distributions. And if you can quantify the distance, for example, using KL divergence, the closer these distributions are, the better you would trust the quality of your generated graphs. But you may need to add some other criteria, like, for example, that you generated something real and not something, you know, that is not valid. Okay, so you need to check the validity. You need to check the validity of these molecules. And this is another thing. So anyway, so here, basically, it's fitting a distribution onto another one. And these two steps are actually very easy. So the first one is a density estimation. So what we want is to use a maximum likelihood to make P model, okay, approximate P data. So here it's we take the we want to discover the theta star, which is the optimal parameters of our model, where we take the average. So on average, okay, or if we sum all these probabilities, we want to the P model to approximate all samples in the data on average, because we're taking the expectation here. So it's sort of an average, okay? And here the idea is that for every single, G in our data, we want to regenerate it, using the theta here. And if we have the theta that is able to regenerate the G drawn from this data distribution P data, right? Then we have solved the problem quite nicely, okay? So the goal is to find, as I said, the parameters theta star such that for the observed graph points, GI for all observed graph points, if we have 1,000 graph points, right, as initial training set, what we want is the sum over all these points of the log, the probability that is returned by the model. So the density that, probability density that we have here has the highest value. So we want to maximize this among all possible choices of theta, of course. So here we can flip this and we can say theta star is minimizes, okay, theta, if we take the negative of the expectation or the negative of the log, and then we can turn this into a minimization problem. So these are two different ways of formalizing this problem. And the goal is, as I said, is to find the model theta that is most likely to have generated the original observed graphs G, okay? So now the good thing, this is called self-supervised. Why? Because you have here the distribution, you have G, right? And what you want to do is you're taking the data itself to regenerate itself. So, a self-regeneration. So I'm using the data here. Well, I'm oversimplifying, of course, it's the P data here, the distribution, right, of the data. And I'm trying to learn the theta star that allows me to create, so I'm going to use a different color. I want to learn the theta star that allows me to create this distribution, okay? Again, so it's self-supervision, and this is why we call it self-supervised, because we use here self-supervision. Some papers called also unsupervised, but I prefer the word self-supervised here, okay? So now the last step after we learn the theta star, so we have our theta star, so all is good. We have our model, we approximated very well here. Now we can do the sampling. So to do the sampling, there are different strategies, but this is one potential strategy. And is first, we want to sample from this complex distribution that we learned, okay? So the most common approach is to sample from a simple noise distribution, which means we take ZI, which is the normal distribution here, and then what we do is that we transform the noise ZI via our deep neural network function or GNN function, which was trained, of course, or optimized on the input graphs, right? And then we pass it through this function, and then we're able to generate a new graph. So here, by taking a noise, some noise kind of, representation or embedding, we pass it through our network. And this vector, actually, when we pass it through the network, we will get the new generated graph. So we will see how this works. It may be very difficult to digest at first, because here what you see is that you're having noise, right? And noise is like a random vector that looks like this. And this vector has values 0.8, maybe 0.1, 0.52, etc. And what you're giving to your network, you're giving noise, and you're getting something that looks real. So how is this network training? So this is the key idea. So how to train, F, how to learn F in such a way that if we give it some noise, right, and giving the optimal parameters that we have here of our, model, the model that we have learned, how can we get new graphs? So imagine these graphs right here. So these have been generated, each one of them from a random noise or random set. So we'll look at this in a bit. And Yeah, so these were the two sections. The first one is on a few examples, unsupervised, generative GNNs, and the second one on unsupervised, where we had the self-supervision here, the self-regeneration or self-supervision, where we try to match the input data itself. So we don't have a target data, we have only the input data that we're going to use without any extra information to do the generation for here at this stage. Okay, cool.